So what I want to do is I want to actually define something called a main diagonal of the matrix. And then we might say, yeah, so could you guess what the main diagonal of matrix A is? We just said it. It's the set of all A, I, K such that what is true? Such that I is equal to K. All right. What about the non-diagonal entries? A, I, K with what? What would you say non-diagonal entries must be true about those? Yeah, that the row index does not equal to the column index. Could you guess, so these are all different definitions that we're going to come up with. Could you guess what a diagonal matrix is? And maybe we'll say for now, so formally speaking, you could do diagonal matrices that are non-square, but that's very weird, right? That would be a rectangular matrix whose diagonal entries are non-zero, and all other entries are 0. So formally speaking, when we say diagonal matrix, usually we mean what's the shape of the matrix. Is a square matrix, could you guess what we say about that diagonal matrix? What is 0? What's non-zero?
0 is non-diagonal.
With all non-diagonal entries equal to what? So the way that we write this here is we would write D, and then D11, D22, all the way down to Dnn. What do we know about every single other entry of that matrix? All zeros. Why is that what we might term a diagonal matrix? What's the only thing that shows up that's non-zero? The main diagonal. These are central to the standard eigenvalue problem. These will show up all over the place. They're the sexiest matrices. If all the diagonals are non-zero, they're the most beautiful matrices that we have access to. Because they're non-singular, they're really easy to invert. There are so many beautiful properties if the main diagonal has non-zero entries on it.